In this video, we're going to devote the entire time solving a Bernoulli initial value problem. And we're going to, after finding the particular solution to the initial value problem, we're going to determine its interval of existence. So let's see how it goes. So here's our differential equation, and we can see it has the specific form for our Bernoulli type, right? Because we see our y that's raised to a power that's neither 1 nor 0, right? And again, if you try to do, if you try to separate the variables, like writing the differential equation in normal form and trying to factor it so you have a function of x times a function of y, it's not going to work, right? And it's definitely not linear as in its given form, but we will now transform it into one that's linear and then solve accordingly. And then after getting the general solution, we're going to use this information to find our constant, right? So go from the general to the particular. And there are many instances in differential equations where you end up making assumptions about your independent variable. In this case, we're going to assume that our x is always positive, right? Nothing wrong with that at all. It might help us in terms of simplifying somewhere along the line. Let's see what happens, right? So first, we're going to identify our n. So here is n. And then we're going to use the standard substitution for a Bernoulli equation. We're going to let u be equal to y to the 1 minus n, which in this case is 2. So this says that u is y to the negative first power, which then implies that y is u to the negative first power, because the reciprocal of negative 1 is still negative 1. So this is a nice quick interchange. And then based on this, I can write down what dy dx is. So just remember to differentiate implicitly. You have to use our chain rule. So dy dx in this case is negative u to the negative 2 times du dx. And this is right where we use our chain rule, right? So we have everything that we need to convert the differential equation into a new differential equation, but where the dependent variable is now going to be u. So first for dy dx, I'm going to write this expression down. So negative u to the negative 2 times du dx plus 4 over x. That coefficient doesn't change. The y changes to u to the negative 1. And then the x cubed coefficient doesn't change either, and then we'll now have y squared, so that's this squared. So if I take u to the negative 1 and then raise that to the second power, I will end up having u to the negative second power, right? And so this is kind of our first step. It's still not in the standard form for something that's linear, but let's go ahead and use algebra and simplify this. So if it helps, you can rewrite terms that have negative exponents. So we can write that as negative 1 over u squared times du dx plus 4 over x times 1 over u. And then over here we'll have x cubed over u squared. So what I need to do is to multiply both sides. In fact, what I will do is just put big, brackets there and just say I'm going to multiply the entire equation by negative u squared. Because remember, in so many of these forms, whether it's a solution or some kind of theory, we need the leading coefficient to be 1, right? So if I multiply through by negative u squared, I'll have du dx, and then this plus sign becomes a minus sign. I'll still have my 4 over x, that doesn't change, and then I end up having just u squared over u, which is u, and then this last term on the right hand side, the u squared completely goes away, but I have a negative in front of it, so I have negative x to the third power. All right, and this is now linear. So we're going to switch gears and now look at our integrating factor, which is our mu. So that's e to the integral of -4/x dx. So this antiderivative is e to the -4 times the natural log of x. Now I don't need absolute values here because remember we're told that we can assume that x is positive. So no absolute values there. Bring up my -4 coefficient. So I have e to the ln of x to the -4. So then the e and the ln, those are inverse functions, and we're left with x to the -4 or 1 over x to the 4th. So that's our integrating factor. And then we take our integrating factor and multiply the entire equation. So now, if it depending on your preference, whether you want to multiply by this with the -4 exponent or the 1 over 4, that's up to you, right? Let's say we take the x to the -4th. So x to the -4th times du dx is x to the, that was a strange little mark there. So x to the -4 du dx, and then minus, now I'll have a 4, and then when I have x to the -4, and then also divided by x, that's x to the -5, then I'll have my u, and then on this side, when I multiply -x cubed times x to the -4th, adding those exponents and keeping the -1 coefficient, I'll have -x to the -1. All right. Now, if we look closely on the left-hand side, we can see our product rule, right? That product rule in reverse. We have our f there, and then this would be f prime. And then there's our g, and then this is g prime. So there it is, our product rule. And again, it's a nice thing to look for it, because you can get into this routine of just going through a process, but when you miss the key concepts, then it makes it harder for you to identify if an error has been made, right? So always look for these little check marks of approval. If you say, yep, you're on the right track, keep going. So then the left-hand side can be written as the derivative of this product. What is the product? The x to the -4 times our unknown function u. And then on this side, no change occurs just yet. All right, so we're looking good. And then, so again, taking antiderivatives of both sides, I'll have x to the -4 times u is the antiderivative of -x to the -1 dx. So this will give me x to the -4 times u. Now I'll have negative. Now this is 1 over x, so we get another ln, right? So we have the ln of x, and then we'll have our plus c, and then multiply both sides by x to the 4th, and this is what we'll have. We'll have u is equal to -x to the 4th natural log of x plus c x to the 4th. All right, so this is our general solution, but this is the general solution for u. But remember, u is equal to y to the -1, right? So I'm gonna, in fact, let me do this. Let me do a couple things here. So I'm just gonna write this as x to the 4th, and then I'm gonna put the positive term first. So that's our c, and then I'll have a minus ln of x like that. All right. So remember, u is equal to y to the -1. So I'll just replace u with y to the -1, and then that's equal to what I have written there in factored form. So x to the 4th times c minus the natural log of x. All right. All right, so good. So this is our general solution, but now we have an initial condition, and the initial condition, it says that when x is equal, let me write this down. When x is equal to 2, y is equal to -1. So this gives me an equation. So if I have -1 to the negative first power, that's still -1. 2 to the fourth power is 16, and then in parentheses I'll have c minus the natural log of 2. Now, this was in part why factoring it will help, because now I can fairly easily solve for c, right? So so divide both sides by 16, so -1 over 16 is equal to c minus the natural log of 2. So then add the natural log of 2 to both sides, and then we'll get that c is -1 over 16 plus the natural log of 2. All right. So what are we going to do? We're then going to plug the c back in, because that's what we need to do. All right, so let's do that. So we have y to the, let me give ourselves a little bit more room. Y to the -1 is equal to, and then I have x to the fourth times the quantity. Now, since the natural log now is positive, let me write that as a natural log of 2 minus 1 over 16, and then minus the natural log of x, right? And then, so this is we're almost there as far as having the particular solution, but we now have to take the reciprocal of both sides. So I have to take the reciprocal of this whole thing, right? So therefore, y of x, my particular solution, is 1 over all of this. X to the fourth times the ln of 2 minus 1 over 16 minus the natural log of x. All right. Now, so this would be a good answer, but since we're going, the question also wants us now to find the interval of existence of this, right? So it would help if we simplify this function a little bit further, right? So the first thing I'm going to do is to multiply the top and the bottom by 16. That will get rid of this 1 over 16, right? In fact, what we could do, and I'll do it in stages. So let's first multiply the top and the bottom by 16. So I'll have 16 there. If I distribute the 16 in the denominator, I'll have x to the fourth outside, and then I'll have 16 times the natural log of 2 minus 1 minus 16 times the natural log of x. All right, so there we go. And we can actually, let me do this. Now, we have two terms in the denominator here that are negative. What we could do is we could multiply the top and the bottom by -1 and do this. And again, I'll distribute the -1, and then that will make it, I'll write it as 1 plus 16 natural log of x, but then this coefficient becomes negative 16 the natural log of 2. All right, so there we go. And then what I can do, I can combine these two logarithms into one. So I'm trying to make the denominator as simple as possible, so that when we look at the interval of existence, the algebra isn't too bad, right? So then I'll have plus 1 plus 16, and then the ln of x minus the ln of 2 is the same as the ln of x over 2. All right, so let's see if we can figure out So let's first figure out the domain of this function. Right? So the domain here. Now, certainly x can't be equal to 0 because of this factor. We see that, right? And then because of the ln, right, the x has to be greater than 0, right? Which actually was a part of the assumption in the first place, and we're kind of seeing why that assumption is valid, because for this part of our function to be defined, right, x over 2, in fact, let me write it like this, x over 2 has to be greater than 0, which means x has to be greater than 0, okay? But the other thing too is we have to make sure that what's in the parentheses cannot be equal to 0. So that's another constraint as far as the domain is concerned. So we have to figure out, or let's say it this way: we'll have to determine the possible values of x so that 1 plus 16 natural log of x over 2 is not equal to 0. So let's do that, and then try to figure out what x cannot be, right? So if we subtract 1 from both sides, so we have 16 ln of x over 2, that's not equal to negative 1. Divide both sides by 16, so the natural log of x over 2 is not equal to negative 1/16. Then do our e. So that means x over 2 is not equal to e to the negative 1 over 16, and then multiply by 2. So x cannot be equal to 2e to the negative 1 over 16, which is just a little bit less than 2, right? So let's put this all together, and I'll state the domain. So x has to be greater than 0, but then it can't be 2e to the negative 1 over 16. So let's put this all together. So it's either this interval, so as far as the domain, it's this, right? Or, and then x could be greater than 2e to the negative 1 over 16. But because this is roughly 1.9, right? So this is essentially at approximately 1.9, this function has a vertical asymptote. So it's going to split into these two branches. So which branch, right, will have our initial condition? Our initial condition is when x is equal to 2. So it would have to be in this interval, right? So the interval of existence of the particular solution is x greater than or equal to, not greater than or equal to, but x is greater than 2e to the negative 1 over 16, right? Because this is the interval that contains our initial value of x, right? X equals 2 is in this interval, not in this interval, right? So there you go, full solution of a Bernoulli equation and working with an interval of existence. It's a little bit harder. It's a little bit harder simply because we had, these transcendental functions, the natural log, and ended up using e and so forth. But the concepts are the same. So this would be a good example, that you maybe work through on your own, and then go back and use the video essentially as your answer key. So I think we can now put our Bernoulli equations to rest and move on to more fun. See you in the next video.